3, 2, 1, go. And we're live. This is Retraice segment number 95 for Monday, December 26th, 2022. At 10 p.m. Eastern, 7 p.m. Pacific, Retraice is about what's going on out there. The short answer to that is computer control. The long answer to that is too long for right now. What are we doing? Best first search, PriorityQueue. We're wrapping up PriorityQueue today. Yesterday, I left it in a bad place. I don't feel good about it. It was a mess. What am I talking about? Well, let's have a look here. So where is it? I gotta go twice. I don't know why I have to go twice. This is where we left off yesterday. This is what you would have seen. This is what would have disappointed you, at least if you're like me. This is a mess. This doesn't help me. This doesn't inspire confidence. This is a mess. We need to make this pretty. We need to prettify this. This is the chatty output from best first search as of Retraice 94, right? Re95, yeah. So let's have a look at a better version of it. So here's the source code as usual. This is the same file seen through 3 different windows up here. The top part is Emacs, and then down here we're going to be running in IPython. Yesterday I talked about all the print statements that I added to help us understand and walk through this best first search. And then also I've added them over here. And this is new since yesterday, and I've added coloring and all kinds of fun stuff. We'll be like little kids coloring. Okay, so first we're going to reset our IPython. Yes, we want to do that. Then we're going to load our, Re95 Pi file. Let's do that. Let's just run a problem. So best first search, let's do, I modified it a little bit so f is no longer a function. I had to specify, I'll explain why f of t or ft is the function we're going to be using. Let's have a look here. Actually, let's do it like this. And nope, and there. Look at that. That's better, right? This is a bit easier to follow. So we start at the top. First, we just print out, I don't need to highlight it, it's already colored. The node after instantiation of class node. So this is the first node. So we're passing it, our problem, I'll put this down here, and actually, what's the, okay, let's have a look here at what our T problem is. Okay, it's this. So we're passing it A to Z. So our T problem is a route problem, is an instantiation of route problem. We're getting from A to Z using the T map, okay? So when we see up here in the first line that the node that's instantiated by, that's an instantiation of the node class, and that's instantiated by our best first search here, okay? We're printing some output to, actually you can't see it there. There you go. That node right here, this node, okay, is this. Oh, geez. It's that thing that I was almost ready to point to. This here, okay? So that's what's there, and that's going to be the pattern that we follow the whole time down through the output of this running of best first search. We're giving it the problem argument. We're giving it the evaluation function, ft. Now here's what happens in PriorityQueue, the initialization of or instantiation of a frontier. Okay, so PriorityQueue, as I said in the, is it in front of me? I don't think it is. In the subtitle for this segment, frontier is a priority queue. Okay, priority queue is a class. Frontier is an instantiation of that class as an object. And I really think, like, just, not understanding PriorityQueue, at least to a certain level of resolution, is to not understand best first search. I mean, that's the whole game. I mean, let's just have a look here. So down here is where PriorityQueue gets called. Frontier is the instantiation of a priority queue, and it's given the list version of our node. I think that's what the square brackets means. And then the key is F. Ooh, I gotta change that. Oh, no, I don't. No, I don't. It's taking the argument from up here. So when I'm passing this F, it's being passed as FT, so I don't have to change anything. And what happens? So we go to priority, oh no, let's do class here we go. And so here's the initialization. It's all chatty now, very chatty, because like I wanted to get the format right in the output that you're seeing here. Like I wanted these things, you know, to be lined up, to have sort of an indent, because they make them really easy to compare. Like you can see here that the frontier.items is the same. It's actually normally in reverse. It's normally yellow then pink. So let's look at this one. So priority queue self.items after a call to self.add of a priority queue. Okay, this is we've instantiated a priority queue, but we still have code in there that's going to tell us when the methods are called, and then to tell us what the new items in the instantiated priority queue look like. That's what's going to come out here in yellow. So anywhere you see yellow is priority queue being called, and then what's different about priority queue, or let's say not what's different, because I'm not doing it before and after. That's a bit too chatty. We're just looking at the items after the call to priority queue, and they're almost all calls to the add method. Okay, this here. But down here, we get things more interesting. We start comparing, okay? But anyway, so after you do a call and you add something to the instantiated priority queue, you check the items, looks like that. Why is this the same? Because that's exactly the same data in memory. Frontier is an instantiation of priority queue. To look at the frontier.items is to look at the priority queue self.items if frontier is an instantiation of priority queue. Okay, so those are always going to be the same. Then after then we get into the loop here. So this is everything before this line is before this loop. Whoops. And what are we doing here? Okay. And no. Okay, so there's not the while loop, but this is the for loop. I didn't mention being in the. Actually, I should. Should I do that? I should just do that. Let's do that. This is because we're going to use this code later. I think this is going to be very useful when we run other. Well, there's another best first search we're going to run best first with tree search in it. I think, but okay. So let's. Gosh, I'm just going to do a print. I'm not going to colorize it because I got to be consistent in my colors, and I think I have a spare one right now. Whoops. Okay, so let's say just entered while loop. Okay, and let's do this again and see if we can just see exactly where the while loop gets entered. Nope, I don't want to do that. Reset, there we go. Yes, and load, and yes, and best first search. Just this is the best first search call to T problem and FT that's in the file itself. Actually, no. This is going to work. I'm going to give it whatever arguments we want in a second here. Don't worry about that. Okay. So I was going to say something, then I decided not to. Okay. So where is? Hang on. Does this look exactly the same? This better look exactly the same. Priority queue begin init. Yeah, it does. Okay. Okay. So where are we entering while loop here? Okay. So right after priority queue length method is called, then we enter the and I don't. Why is it calling the length method there? I mean, this is the. Yeah. I mean. Oh, problem.initial. No, that's reached. Frontier. Okay, well, that's just, again, I got to see if, we got to make sure that everything makes sense. Everything must make perfect sense. Yeah. It gets called right here. Okay, so before we added the little print statement, before we made it chatty down to the while loop, we had the priority queue length method being called. And then again, down here, after we add the while loop, it's the thing that happens just before. So there's some stuff that happens between. Why is wait? Why is the length method being called after? That's because to instantiate or to let's say initialize the reached dictionary, you're passing the A node. No, that doesn't make sense to me. Okay. Oh, don't. Oh, wait. No. Between here and here. All right, let's just highlight it. Why is the length method being called after the reached? It's got to be because reached is, I don't know. Damn it. Why? Problem.initial is a dictionary. Reached is a dictionary. And you're putting the initial state in there and then the node. Why would you need PriorityQueue to do that? What the crap? I don't know. I'm going to have to leave that as a mystery. I'll figure it out when I'm doing the notes. It's always easier to figure things out when I'm doing the notes. Okay. Just leave that as a little mystery for me to solve, that why this is being called there. And I'll just screenshot it so that I don't forget. Oh, great. That's what I wanted. I got my screenshot. Okay. So then we're in the while loop. And what do we do? Before we get into the for loop is this stuff. Okay. So we're going to check the node. It's the same, right? It's the same as the node was here. Yeah. Okay. So this is node right at the beginning when we initialize it. This is it after the while loop, but before the for loop. Frontier.items looks it's the same as it was when we instantiated the PriorityQueue, instantiated Frontier as a PriorityQueue. And then PriorityQueue gets called. We're going to pop the top item off of our Frontier.items, which is a PriorityQueue. So we could call the pop method, and then we since there's why son of a bitch. My feedback is working too well. It's making it clear to me that I don't have a perfect understanding of the execution. I'll leave that with me. Why? It's working. I mean, I should say, like, don't lose confidence. Like, the program's working, but I have not combed through every line of this, like the order of it. Obviously, this is not going the way I planned. Anyway, okay, so let's keep going. Let's just not get hung up on little things that I fail to understand in the moment. Okay. Frontier.items after the pop. Oh, no, it's right. No. It's right. Why is this? But shouldn't that be? So this line should match this line after the pop. It doesn't. Frontier.items before the pop. Okay. Then the pop happens. Then. Okay. So when a pop happens from. Oh, come on. From PriorityQueue, we're doing the pop method. Oh, wait a second. You dumbass. I know why I did this, though. Okay, look. I put the print message here, okay? This is why. This mystery is solved. I put the print message there because I can't put it in the method, that defined pop method. I can't put it after the return. So I can't actually print the items after. That's probably why the other one was too, right? I hope you're following me. So if we... What was the other one? Oh no, that was why was the length called. Okay, but anyway, if I can't put this, like after the method gets to the return statement here, after it makes a change by actually calling heap pop here and changing the heap, then if I call, then I get this print statement will be outside of the, at least as far as I know how to do it. I guess I didn't try just indenting it, but I couldn't get my environment to agree with me. Let's do this. Why not do it? Let's just see what happens. Okay, and that. Don't make a liar out of me, please. Don't make a liar out of me. You're crazy. I swear that didn't happen yesterday. All right. Okay. Reset the scoreboard. We are not doing well. Luckily, this is a home game. All right, load. Okay. Best. Okay. And we look for new things. I don't even know where it was. Okay. The pop method was called. Yeah, see, it doesn't happen. I don't know where it's happening now, but there's no self.items for priority queue now. Yeah, so it's happening somewhere stupid that we don't want it to happen, probably down below somewhere. But like if you look at this, you've got just after entering the while loop, okay, or this is the while loop. I mean, the whole thing below it is the while loop, but it's before we get into the for loop, you're popping from priority queue, okay, and you can see that node after the pop, because it is that priority queue. Its node is the not node, but frontier. Node after the pop. No, sorry, frontiers. Before the pop is 45A node, and after the pop is 0. Okay, but we're surprised. Not surprised. I told you it wasn't going to work because we were hoping that just indentation would give us this line, but after the pop, and so it would be empty. Okay, so that it would match this frontier.items because they're the same data, but I can't do it. I can't do it, and I gave it the good old college try. Okay, that now, and let's just doesn't work. Okay, so are we starting to feel more confidence? I am. I don't know about you guys. All right, so what happens? So we're in the while loop. We're just basically all we're doing is popping, setting the node equal to the first item in the frontier heap, the priority queue heap here. That's line 127, okay? And then we're just printing to confirm that we know up from down the node itself, and then the node after the pop, so it's a new node because we changed it. I mean, it's not necessarily new every time. Like it's not new in the beginning because the first item in frontier, which is priority queue, the instantiation of priority queue, is the same as the node that corresponds to the state that we passed when we initialized node, when we instantiated a node as node in the beginning. So there's no change there except to frontier, okay? Probably an inefficiency in the code, but we didn't write it and we are not smart enough to be sure about that claim about inefficiency. Okay, can we get into the for loop? Can we just calm down, all right? All right, so what did I say, for loop? It's not a for loop yet. It's never a for loop. Why do I keep saying for loop? Did I write for loop when there wasn't a frickin' for loop? Dude, this is a disaster. Where's the... am I in the right place? What am I doing here? Yes. While, if... Oh, here's the for. This is the for. This is the for. Oh, jeez. Man. I'm really well rested. Like, I'm telling you right now, this is not sleep deprivation. I got caught up. I'm good. I don't know about anything. All right. So, there's a conditional here. And we just print what? Oh, this is just the state check thing. This is just the state check thing. We're just checking the goal to see if we've already got the goal. If we've already got the goal, we don't need to go harassing people's children down here. Okay, we've got what we wanted. We can leave town and be happy. But if we don't have the goal state, we got to go around harassing parents and children until we find it. Okay, so this is the goal state. Did I print anything in there? Yeah, I printed. Oh, yeah. Oh, that's the nice formatting. So when we get down to, when we finally do find that goal state, we're going to have all this nice formatting for the data that we wanted in the beginning. That is the data, that is the presentation of the data that we wanted in the beginning. When I did that first run of best first search and gave the arguments and it didn't throw an error, and I got excited and I was like, this can't be right. This just says blah. And it was, what I was looking at was Pacman, dada, so that means it's a node. Okay, if it's data in single ticks, that's the state. That's what we want to get to the state, but we don't need, that's not the data we want. What we want is the node. But really, what about that? Is it just the word data in Pacman? No, of course not. Okay, that's the node we want to get to, Z node. This is not, now we're moving to A to Z. We're not doing data. That's why that's not our goal node. Data is not our goal node now, but it was back then. What state does it correspond to? Well, that's obvious because there's no complexity to that particular labeling. What's the length? The hops. A to Z is one hop because if we look at our map, just our sanity check map, is that one? Oh, I'm getting good at this. I'm going to get really good at switching to this thing right when I don't need it anymore. A to Z is one hop, so that inspires confidence, okay? And The parent node was A. That makes sense. It's kind of boring information, but it makes sense. The action applied to A was Z. That also makes sense, even though it might be confusing to the noob. And the path cost was 75. Okay, looking good. Anyway, that's what's going on here. This is the state check, and return the node if you found it. If you're at the goal state, return the node that you have when you get there. Okay. Now, that's not. We have to check for that, of course, but that's not really where the action is. The action, in my opinion, is really in priority queue, but it's not really. It's in best first search overall. And the for loop is the thing, is the action. Again, like I'm sorry about the width of this. These lines, but I just did it because without that width, all this data is not going to line up in whatever this is, like column 60 or whatever, wherever we're at right here. To make that line up like that so you can do easy comparison, I had to, go crazy. So for child and expand, so we're using our expand function on the node given the problem, or with the problem and node as argument, and here we're printing the S value, which is the state, the child state of the node that we were at. So our new node, okay, so we have to print all the children of the node so we can compare them before we take an action. Not print them, we have to analyze them. Okay, so what are we doing? The while loop, the node after we pop it, in the first case it's boring, it's just the same node again because that's the one that was on, that was in our custom heap. Now we're in the for loop. Child state is Z, okay? That's the first child state. The child states that we're going to go through on this first, that are applying expand to the A node because of, bear with me, because of search T locations, no, not T locations, T links. A has 3 different actions available, okay? A to Z, A to S, and A to T. So that means that there are 3 child nodes if A is the parent node, okay? And they each have their own action costs as well, okay? So the first we're going to analyze is Z, the next one is S, and then the next one is T. And then at the end, we're going to decide on one. Can you guess which one we're going to pick? We're trying to go from A to Z. Can you guess? Should we pick S? Should we pick T? No, of course not. But we have to analyze them all first because our algorithm is slightly under-optimized for that. If it finds, there's no check. Like to make this work even more brilliantly, we would, no, I don't want that. No, wrong way. We would maybe put a little check in right here between 38 and 39 to see if the child state that we just got from the expand function is one of our goal states, right? Just like up here, we have a is goal check. We should have one down here. Maybe we'd write that, but no, we're way over optimized on this thing already. There's no way I'm writing that. I might write it. Sometimes I do things I say I'm not going to do. Sometimes I don't do things I try not to do the opposite. Okay, so let's analyze Z. First, what is the reached list of nodes? Well, we've reached A. We started at A, and we've reached Z. Hello, McFly, you're there. Why are you going to do a bunch of lines here? But anyway, okay, PriorityQueue self.add method is called, and we're going to add the new node with a cost of 0. Again, McFly, the cost is 0. That's, by the way, you haven't seen this yet. I did this this morning. So I'm using, the reason that these don't just say FU, which started to feel kind of rude. Like it was funny when I started, and then it's like, man, half my screen has a bunch of FUs on it. I feel like I need to act a bit more mature. Okay, so I changed it to an actual F function. Let's have a look, shall we? Def FT. Yes, that's okay. They're all the same, but I gave them different names for reasons I'll explain in a minute. I just borrowed this from some of the. Did I borrow? I borrowed. Not really. So basically, our F evaluation function, I'm calling it FT for reasons I'll explain, takes the node and applies. Does it take the node? What's the argument to? It takes. Is it actually a node? Class. Prior. Okay, so here's where F becomes key in this when you instantiate a priority queue. So self.key is key, and we use the key when we push onto the heap. We start using heapq, which I don't know much about, but that's what we're using. Okay, so where is it? It's like always right in front of my face. Okay, so self.items is a list. And we're going to, for item and items, so we have right now, when you initialize it, it has like one item, but then that changes over time. We're going to add the item to the self, and where's the thing that I thought I would see? I guess it does that. Oh, no. We do add down here. Yeah, this is where it starts to get interesting. The items pair. The items, the pair. This. Okay. So key of item right here. Got this? I know it's kind of hard to follow, but key of item, that is calling our evaluation function on the item, and then making a little tuple out of that, so that when you push something onto heapq, okay, which is inside of PriorityQueue, which is our what is it called again? I've forgotten. It is our frontier. Then you've got a pair. What does the pair look like? The pair looks like it looks like this. It looks like these things. Where's my 0? I was dealing with this one. It looks like this. It's this tuple, this double, okay? The first number is the result of the f function, the evaluation function applied to the node, okay? And what I'm doing is I'm using defft, just returning the rounded version of the h method of it on t problem given the argument node. What is the h method? Reverse h stuff there, okay? It's this. So I thought for a while that these little compound statements were only going to be relevant when we started doing informed heuristic search, but actually they're relevant unless you want to just put a dummy f thing that returns itself, or returns whatever argument you pass to it, or returns some some dumb number, or a constant that has nothing to do with the input. You have to use h. You have to use or something equivalent to h. So what we're using here is just what they have in the implementation on AIMA Python, which is this return some absolute value, and then calculating the straight line distance. And I'll show you in a second here what it looks like, the arithmetic of that, which I've checked on a few things. Okay, but anyway, h is helping us do the straight line distance down here. Not helping us; it's doing it for us, and it's helping us decide which way to go when we're at a to z. When we're at a, and we've got the opportunity to go to straight to z via 75, or then to s or to t. We don't have a check. We don't have a check there in our code, as I just mentioned, that would tell best first search, hey, you found it. I think what that means is if we didn't have the evaluation function, it might not get there as efficiently. It might not get there in the first step. We could test that, but this is going too long, and we're doing a double header. Oh my God, we're running out of time. Okay, double header might be late today. Okay, so anyway, that's what's going on there. That's what these scores are, and I've checked the arithmetic on these. These are good. They're rounded. They have to be rounded. But the T links? No, not Linux. Not T Linux. Linux with a... Oh, come on. Oh, no. Links. T. I did that before. No, that's just suspended. Look at all those. Look at this. Look at this. I was trying to use the calculator, one of the built-in calculator systems in Emacs, and I crashed it like 3 times. That's why I've got it in a separate... Okay, anyway, that's not what just happened, but I thought it was. Okay, so these... crap, what was I talking about? Yeah, the straight line distances between these, not the locations. The straight line, these are XY coordinates, right? Okay. The straight line distance from A to Z, okay, is 0. I'm sorry, once you're at Z, the straight line distance is 0. The straight line distance from A to Z is what we find out in the beginning, which is this is 45. Okay, that's this here. A to Z, okay? So we take the XY coordinates and we use simple Cartesian geometry to calculate the straight line distance, and it's roughly 45. And in case you're wondering if I did the math correctly, there it is, okay? I didn't do the math. I never do math, correctly or otherwise, on my own. I make machines do it unless I have no choice, okay? So we have a score, a distance score, an evaluation function score here of 0. It's very low. You want this to be low. That's also how priority queue is implemented. Because it says here, it says up here, a queue in which the item with the minimum F of the item with the minimum F of item, i.e. the minimum score, is always popped first. So that's the way they've implemented it here. Can I show you exactly which lines accomplish that? No, I haven't gone into heapq, because I got to stop somewhere. But that's what we're getting here. We want the lowest score. Now our score for this first child node, Z, which is also happens to, of course, have a state of Z, which is our goal state, and our stupid best first search is too dumb to stop. That's okay. I still like you, best first search, but this is ridiculous. Is 0, so that should have been assigned, McFly. Okay, but anyway, frontier.add is called, and just like PriorityQueue self.add, because they're the same thing. And they end up in the same state. Who would have thunk it? Okay, so we do the same thing 2 more times, one for each state. We did it for Z, Z. Now we're going to do it for S. There are a few S's, but not S spaces. Oh, I suck. Search there. Okay. And then we're going to do it for T, and then we're going to call the length method again. That's checking, right? It's checking the number of hops. Where is that? What is that? I know where that is. I feel like I know where that line is, why that's doing that, but I just didn't notice it earlier. But I know, I'm not doing that. We gotta keep moving. Okay, trust me though, it's working. I'm going to show you in a second. And don't trust me. That's why I'm going to show you. Okay, so then we've evaluated all of these child nodes, and our list of our priority queue list has put them in order. Okay, that implementation, their clever implementation, puts them in order so that the top of the items heap is the lowest cost, and then the next one is 122, and then the next one is 125. And these are the straight line distance. Why don't I have those? Oh yeah, I didn't do all these. I did A to S, so that's 116. Okay, so you can. Oh no, that's we're from Z to. Our node is at A node Z, cost to 0, cost to, oh, come on, you kidding me? Why is that wrong? 122 to get from A to Z. Well, I know this works when we were going from, what are we seeing here? Why is that 122 and 125? These are the straight line distances from the node that we're at to these other nodes, 122 and 125, 140 and 118. God damn it, I did this earlier today. Why? Oops. I'm going from A to Z. The path cost, oh, no. Straight line distance is not the same as path cost, but it should be in this case. How are we calculating straight line distance? Based on the coordinates. Oh, you know what it is? I can't prove this because it'd take me a few minutes to do the arithmetic. The coordinates that they put in that thing are not true to the to this map, or to the where is it? Don't look at me. Look at this. I'm pretty sure the reason that these are going to be is because the coordinates that they. Oh no, it's not they. Did I do it or did they do it? I don't remember now. But that's my hypothesis about why the path costs of these other don't line up with these. Or the straight line distances don't line up with the path costs. The straight line distance from A to S should be 140 if our coordinates are true to this map, but I bet they're not. I suspected that when I first looked at the implementation, but I can't prove that to you right now. But anyway, these things are definitely being sorted correctly. Whether or not whatever the cause of that is, we're going to see. I don't know. I keep having to make all these qualifications. I think I'm losing your confidence. Doesn't matter. You don't have to have confidence in me. The source code is out there. And then the length method is called to check the number of hops. Okay, so that's what's going on there. Now we are back in the while loop to check to see. So basically, at this point, I'm pretty sure it's this line where the for loop chooses the child state for loop chooses the child Z node because it's the lowest cost. It's all these zeros. Okay, those zeros. So it doesn't choose, like we order them in the heap, in the cost state heap in priority queue, which is frontier, in a way that so that when we take the top item off of that heap, it's not a stack, it's a heap that we've ordered. So it's like a stack, but it's prioritized, and also this corresponds to like the I don't know if I can get to it quickly. The source code, well, it's 190.82. It's this ordering that we needed to do. Okay, frontier is a priority queue ordered by F. That's our straight line calculating straight line distance calculation. So it needs to be in order for this to make any sense. And the other thing that we're going to find out about this F, this little magic F, is that we change this and we get basically with the same code, we get different implementations or different algorithms implemented just by changing the F. We're going to see all about that. We've looked a little bit about that before, but I am just not making good time. Okay, so we've prioritized the zeros, and we are going to now, after we've checked the length, I still don't know why that's happening. We're going to go back up to our for loop, or our while loop. Okay, we're going to go back up here. Why the hell is it happening? That's going to drive me crazy. And set the new node equal to the one that was at the top of the frontier heap. And then we're going to check to see if it's the goal state, and we're going to find that A node is the node before the pop, Z node is after. If you want to look at the items list after, it doesn't matter, but look at this. Here's your goal. You found it. Z node is the goal. No more work needs to be done. Okay? Now, that's A to Z in our little special space. Let's do best first search on, I said yesterday I was going to do it on the real problems. Let's do it on the real problems. If you look down here, okay, I've uncommented all this stuff. So the Romania map is now in place. And it has been loaded as part of the source. The only thing I've added is these specially named F evaluation functions. I've had to, just because of the way that I'm taking the arguments, and I just can't bother to make it so that I don't have to do this. It's just easier to just, because of these problems, just to rename the F functions for each one. And I can actually mix and match them too. This is kind of cool. But anyway, our evaluation functions are specialized right here. So that when I call route problem, when I do problem R0, the evaluation function uses R0.h, the H method on R0, instead of just like route problem or something like that. It wouldn't work. It wasn't working. It was throwing an error, and it made sense that it would throw an error. Okay, so let's do this. Let's do R0, Romania problem 0, and let's call F0. Okay, pretty easy. So what are we looking at here? This is the whole execution, okay? And it's short because it's A to A, right? It's just, the first problem is their toy problem, which is just get from A to A. So let's do A to B, okay? Let's do our problem 1, and oh, for Pete's sake, and F1, a little bit more complicated, We got to state B with a path cost of 450, okay? We definitely had a priority queue, and the reached nodes is the one that never stops growing. Okay, that always, you see the blue. Okay, blue here's reached. Actually, reached. Okay, these, and can we do regular expressions? No. Come on, that would have been so cool. I don't know. I can do it in Emacs. I can't do it in Tmux. So reached. Each one of these blue lines gets bigger and bigger as we go through the execution. It's not true of. It's not going to be true of the frontier. In fact, they're probably going to be inversely proportional, because the frontier is going to be a perimeter, whereas the reach state is going to be an area. The area is going to grow way faster than the perimeter, but they're going to be proportional to each other. Depending on the shape of the search tree. That's too much math. Mathematical disclaimer. I should not be your programmer, and vice versa. Okay, so reached keeps getting bigger. The reached nodes keep getting bigger as we go down. And where do we start? So our start node is up here. We start at A. This is problem R1 using evaluation function f1. We could use f0 or f4 or whatever. It still works, and you're just calling irrelevant data. You're calling the h method on other problems. So like it would be, if we were to change this to f2, then we would be evaluating our best first search working on the problem R1 using the heuristic as applied to R2 or R0 or R2. I wonder if we could try C3PL. Okay, so we go down through and we get into the child for loop. ZST is where we always start with. When we start at the A node, ZST are always the child nodes. What does it choose? It chooses it chooses S. It chooses S. Okay, so let's go see if that makes some good common sense to us here. So it chooses S. It's trying to get to B. That's a good decision. I mean, that's a great decision, even though I can't pronounce the word decision. Okay, so it chooses S. Now it's going to expand S. What should it find? It should find Fagarash and RV, which will probably just be V, because there's probably an R somewhere, right? No, it's either going to be R or V, but we'll have a look here in a second. Okay, so in for loop, child state is A. Because it can go backwards. It can go backwards. It's not a directional, so it does. But it skips. Oh, it skips. This is cool. So it skips A. It doesn't analyze A. Why? Because there's code for that. There's code for some stuff in here. It's not the best code, but it's pretty darn good. Better than I could write it. If problem is goal, is it that one? No. It's here. If S is not in reached, or the child path cost is less than the value of it having already been reached, then execute the expand. What is it? Where is it? It's reached. No, we've already done the expand above. Now we're just deciding whether or not to execute these if not in lines of code. So anyway, it doesn't expand on S because it's already reached it. And the path cost to reach it is not less than the cost that we've already incurred, or the cost that was. Do you know what I mean? I don't know what I mean. Okay, so then we go on to the child node B, and we analyze B, and there are only two, right? Oh no! Why does it think it can get straight to Bucharesti? Why? Let's look at the Romania map. There. Okay. A to. I've already forgotten. So it's in state. It's in state. It's at S. It's at S, and it doesn't. Hang on. Just entered while loop. Node before is S, and node after is F. So it's at F. I'm losing my train of thought. F. Did it get to F already? Am I looking at the wrong part? S and B. Yeah. I was thinking that we were looking at the S execution, but we're already here. This thing moves fast. Okay. Again, I thought the code was bad, but okay. We have to move, and it continues and on doing what it does. Okay, so I gotta stop because I committed to do something else. Anyway, you could run these. You can see this is all the source is going to be on our GitHub, retrace.com. Did I show you everything? I meant to show you. Like that's I showed you everything I wanted to show you. I didn't go as carefully through it, but anyway, we had fun. This has been segment number 95. Same time tomorrow, 10 p.m. Eastern. And now we're going to do a double header. If I can spin it up quickly enough. Of course I can. There's no if. I'm having doubts up here. You should not be hearing those, but I talk a lot. All right, signing off.